Good afternoon, year 13s. Thanks for coming along, guys. Okay, final lesson of acid-base equilibria for A2 chemistry. And we're going to be focusing entirely on buffers today, looking at it from an exam question point of view. And hopefully this should kind of solidify your understanding in buffers and picking up the method of how you tackle each one of these questions, because there's an awful lot of that, and I need you guys to be in good routines, following good methods that are going to hit all the marks as we go through. Okay, so I'm going to share my screen. Let's crack on. Now, I've put the questions. I'll get rid of that, and I'll get rid of my face entirely, so you're not looking at the I'll then stop the cam as well. There we go. Okay, not that it actually stops it anyway. So these are the questions I'm going to be going through today. A huge booklet of buffers. They're all on the Google Classroom for you to have a go at yourselves. But I just thought I wanted to have a go at some of these in lessons and to give you guys an opportunity to see me go through them. And you guys can have a go at them, then check what I've done. So I'm actually going to start off at the very end of the document, because we've just had a quick 5-minute chat on the Google Classroom, and lots of students had lots of questions regarding the graphs and the regions and how you explain them. And so I'm going to start off with this one. So this question appeared about 3 to 4 years ago, where they gave an acid-base titration graph, and they'd highlighted each of the sections. And they'd said, they hadn't actually highlighted them, but they'd circled them and added a letter. So I've just grabbed an acid-base graph, and it's interesting that this one happens to be got a bit of information on PKB in it. I did want to talk about a little bit of weak bases, but I don't want to today. So in fact, I'm just going to say ignore this entirely. I don't want to, what I will do is, I'm going to do a separate lesson on weak bases. And that way, if people want to watch it, they can, but it really isn't very necessary. But I'll do it anyway as an extension lesson, an advanced extension lesson for anyone who's thinking of going into some form of chemistry or whatever. So anyway, so 4 questions came from this graph, which was to explain each one of these sections. And you can see the marks for each of these particular points. They're mostly 2s, but there's a 3 in there as well. Okay, so question number 1 simply states, explain the sudden increase in the purple region. It shouldn't have said increase, by the way. It should have said decrease. I apologize for that. I'll just put a line through that and put decrease. Yeah, it doesn't actually make any difference. You could have just said a sudden change. Explain the sudden change. So this sudden change is here. Yeah, this section, we're suddenly seeing this very rapid decrease of pH. It drops suddenly and then levels off. So the question is, why does it suddenly drop? I often describe this in my lessons as a tail-in for buffer regions. So why does it? Now it's 2 marks, which means it should be 2 bullet points, but let's just see how many it takes. So the first thing that says is, so why would it suddenly decrease? Well, what are we adding? Well, we're going from this is a weak base. Yeah, we know this because it's starting at pH 11. Yeah, and we're ending at pH 1. This is ending at a strong acid. So we're adding a strong acid to this. So that's the first thing we've got to identify. So we're going to say, on addition of strong acid, the H plus ions, yeah, and this kind of makes sense, the H plus ions react with the, I'm going to put the weak base, react with the weak base. Causing, now, so that's the first mark. We need to say that there's a reaction here. Why was it pH 11 at the beginning? By the way, let's pick out ammonia as our weak base. Yeah, the pH is 11 because I got lots of these. Well, if I now suddenly add HCl, yeah, if I add HCl, I'm going to neutralize it. That is going to happen. And I'm going to form ammonium chloride. Yeah, and the pH, the weak base is going to drop very quickly. Yeah, on addition of the strong acid, H plus will react with the weak base. Weak base will drop quickly. Yeah. Now what we need to do is, so it will drop quickly, but now the clever bit of this question, the bit that everyone misses, is, and the reason why this is hard is because it's linked to the buffer region. So I'm going to come back to this. There's one more bullet point in a mark here that we're going to miss if I'm not careful. And I want to then go into the buffer region. So explain why the pH only changes slightly in the yellow region. Okay, so first thing we need to say is this is a buffer region. Totally reasonable. 1 mark. This is a buffer region. Right, we're still adding strong acid. Yeah, we're still adding strong acid. So H plus is reacting with weak base, However, and this is where it's useful to look at the equation. So the ammonia is reacting with H plus to form the ammonium ion. This is the equilibrium. This is the weak base, and this is the conjugate acid. So why does the pH hardly change? Because in reality, we realize that these 2 points here are the same. Yeah, the H plus is reacting with the weak base. But in this case, now what's happening is the reason why it doesn't drop is because even though we're removing this guy, yeah, even though we're removing the base, what's happening is we're creating a conjugate acid, which is going to therefore push it up. And this is where, with this particular section, we have to, whenever this section of the graph, you've got to use your understanding of the buffers. So H plus is reacting with the weak base, yeah, equilibrium shifts, and in this case, it's going to shift that way, shift left to right, equilibrium shifts to the right, and this is the important bit. Yeah, we are now going to have the ratio of weak base to conjugate acid remains almost the same. The ratio of weak acid to conjugate base remains almost. This is the important bit. Yeah, remains almost. God, don't forget that word. Almost constant. So now we get to relate this back to the original point. So the original point is going to say, so why would it drop quick? The weak base will drop quickly. The ratio of weak acid to conjugate base to CBAS will change drastically, a lot. Yeah, because at the beginning there is no conjugate. I don't like the H. You don't need the Cl minus. Just I shouldn't have done that. Yeah, because at the beginning, this is where I've erased my equation. At the beginning, we had loads of this, and we had none of this. Yeah, none of it. Let's put some numbers in. Yeah, I had 100 of these and 0 of these. Well, these are giving me the pH of 11. Yeah, they're giving me the pH of 11. I add H plus. Yeah, I add the H plus to this. Add H plus. This drops really quickly. Yeah, 90, and there's a massive shift in these numbers. Yeah, but then, so we end up with, weak base. If we wanted to do this, it's going to be Ka equals, it's actually Kb, of course. Kb equals the reactants and H plus. Shouldn't really do it, should we? Yeah, we can do. Yeah, we can do. All over ammonium. Yeah. The water doesn't appear in the equation. I'm tempted to explain that a bit more, but not that it really matters. But at the beginning, because this ratio changes drastically when it first begins. Yeah, and that's a mark that everyone missed. The ratio of weak acid will change a lot. Once you enter the buffer region, it stabilizes. Yeah, you start seeing very small differences in the ratio. Yeah, once you achieve that buffer region, we've got a reasonable amount of them. I hope that makes sense. Yeah. And that's the mark everyone will lose. That there in that one. The reason you've got to say is because you've said it in the next one, which is really weird, isn't it? I know, it's horrible. Next, explain why the red region is almost vertical. Right. So what we need to explain here why it suddenly drops. So what's happened here? We're adding acid. Yeah. Well, at that point there, the conjugate base, which we have, sorry, the weak base. Yeah. So I need to actually give at approximately 80, at approx 80 centimeters cubed, the weak base is all used up. So nothing to react. I'm suddenly realizing I'm getting messages come through on my computer, which means oh no, let's ignore that one. I need to bring up ratio of weak acid to beta. Hang on a sec. Sorry guys, I haven't popped out the chat, have I, on my YouTube video? I've also realized that I've left it running as well on there, which is irritating. Let's pop the chat out. Sorry guys, totally my fault. I'll close that down, save me the bandwidth. Okay, so Ben says, ratio of weak acid to conjugate base. Are we not using HCl with the weak base? Yes. Hang on, sorry, did I say something wrong? The weak acid and the conjugate base. Yes. Because here, Ben, we had lots of weak base at the start. Yeah, color code it. Lots of weak base, which is ammonia. Yeah, lots of weak base. Have I said weak acid? Oh, nuts. Sorry. Yeah, sorry. Ratio weak. Sorry, Ben. Thank you, Ben, for that. Really appreciate it. Ratio of weak base to conjugate acid. Sorry, Ben. Thank you. Easy to get that wrong. I do apologize. It's because I don't usually work on a weak base front. Yeah, sorry, Ben. Thanks for picking that up. I do appreciate it. Yeah, conjugate acid. Thank you, Ben. Thank you for fixing that. Okay, so yeah, so at that point, nothing to react. So nothing to react. So nothing to react with H plus. So H plus in excess, sudden pH change, sudden pH drop. I like it. So we're saying the marks actually come here from saying it's been used up, nothing can react with it, so the H pluses are going to suddenly cause a drop in the pH. Yeah. Explain why the pH change. Explain why the pH change in the blue region. Right. So why does that level out? Okay. So we get this sudden drop of pH as we get down to pH 1, and then it seems to level out again. It's only 2 marks again. So we're going to say H plus is in excess. H plus is in excess, probably 1 mark. Yeah. And then we're saying, hang on a minute. So why does it level out again? Because if you keep adding H plus and nothing's there to remove it, why is it not dropping? It's because in order to increase almost level due to pH being a log scale. You would need, log scale, next bullet point, need 10 times as much H plus to drop each pH number. You need a lot of it. You actually, the mark is just for saying that you require a lot of, once you reach pH 1, almost level to pH being a log scale, once at pH 1, to decrease further further requires a much higher concentration. You can also say that you have reached the pH of the acid itself. Yeah, reached pH of strong acid added. Because what that's saying is that once you achieve that pH, we know that we're adding the weak base at pH 11, we're adding the acid of pH 1. Well, you can't get below 1 then. You can't, because you can't make that more concentrated, because whenever you're adding that to it, you're only diluting it, which means it's as far as you can go. Yeah? So it kind of levels off because the H plus is in massive excess. Yeah? So that's what I would do. It was a hard question. It was nice that they kept the marks as little as possible. They were down 2 3s, etc. But it was tough. Yeah, that was the one that everyone really struggled with. Yeah, why the sudden decrease in the purple region? On addition, H plus reacts with weak base. Weak base will drop quickly. The ratio of weak base to conjugate acid will decrease a lot, will change a lot. So you see this sudden drop, and then we enter the buffer region where we have the conjugate, when we start seeing the buffer interaction taking place, which is why this ratio remains almost constant. Anyway, so, oh my goodness, I've got 25 minutes. Let's see how many we can do. Okay, buffers, calculator on. A third beaker C contains 100 centimeters cubed of ethanoic acid. The acid association constants here. Write an expression for Ka equals H plus CH3COO minus all over CH3COOH. Can I just say, by the way, there was a habit. Some students have picked up a habit. They've read online the idea of using HA or HX as the weak acid. And you can create what's called a generic expression for Ka. You can never use this. Unless you've been given them. Yeah, if you've been given ethanoic, you are expected, it will say on the mark scheme, do not accept HA or HX. You have to mark this for these guys. Yeah? Okay. Calculation, write an expression. So this is Rhea. This is just a weak acid calculation. That's all they're asking. So I can now use my false expression equals H plus squared. I'm going to put that over the ethanoic. I'm going to reorganize this. Therefore, root Ka times the ethanoic acid concentration. Yeah, it gives me H plus. That's going to give 1 mark right there. Input 9 numbers. 1 point, you have to use the Ka that I know my Kas, but they've given me a slightly funny one there. 1.74 multiplied by the concentration of the weak acid, 0.0125. And then I'm going to root that. The volume makes no difference. So I'm going to do it separately. 1.74 exponential minus 5 multiplied by 0.0125 equals root answer. That's going to be a mark. 4.66 times 10 to the minus 4 minus log answer. And I get a pH minus log answer. And I get a pH of 3.33. There we go. Weak acid question only. Next, aqueous sodium hydroxide is added to the beaker until the pH becomes 4.84. Name the salt formed in the reaction. Name, not formula. Rhea, so at the buffer region, ammonia is acting as a buffer by actively taking up H plus ions. But even though that happens at the tippy top first step, it's not a buffer because there isn't an equilibrium there. Correct. That is absolutely correct, Rhea. There is no equilibrium at that stage. If there's no equilibrium, there's no buffer. Add that onto the note down there at the bottom. Why is there a sudden jump? It is not an equilibrium at this point. That there is absolutely correct. Add that. Not equilibrium at this stage. I like just writing that down. It's nice. Not equilibrium at this stage. Yeah? If there's no equilibrium. Now, don't get me wrong. That won't score you this here won't score you both marks. Yeah, you need to talk about the ratio changing to give you the second one. Sorry, just backing up to what you were doing earlier. No, it's absolutely fine, Ria. I really like, it's not above there. So it's nice that's true. That's absolutely correct, Ria. But you need more of a description of what's happening in there to get both. Just warning you. Let's go back to the beginning. Okay, so name the salt. So this is sodium ethanoate. If you do a formula, you're going to lose it. Sodium ethanoate. I like it. Okay, so now calculate the value for the salt ethanoic acid ratio in the solution at pH 4.84. Pause the video, guys. Have a go. So we've got the Ka, which we were given, equals H plus, which is the pH, which we've also got, multiplied by, now this is where I talked about this last time. You can actually separate it out. I'm just going to put over acid. Yeah, so we can rearrange this. So therefore, the Ka of 1.74 times 10 to the minus 5 divided by the H plus. So we need to work out the H plus ions. So I'm going to go 10 to the minus 4.84 to flip me out into, so I'm going to go shift log minus 4.84 gives me 1.45 times 10 to the minus 5. So divide that number by that one, because that's now the H plus concentration. Yeah, times 10 to the minus 5, and I will get the ratio. Oh, yeah, okay, that's fine. So that's 1.74 exponential minus 5 divided by 1.45 exponential minus 5. So the ratio is 1.2. So it's 1.2. So the salt, so the value is that answer. I'm pretty sure they'll give me that answer. I think that's going to be the mark scheme. But it's also nice to put 1.2 over 1. It's always nice to do that in terms of concentration. I don't think they require anything else. Do they require you to talk about the 100 centimeters? Just calculate the value for the ratio in the solution. I think that's okay. Yeah, it's only 3 marks. Yeah, next. Explain why chloroethanoic acid is a stronger acid than ethanoic. It's always nice to see one of these appear. There's chloroethanoic acid. Here's ethanoic acid. So the difference is that we've got a H, we've got H's on the ethanoic, but then we've got H's and a Cl. So the difference is that there. So Cl, switch to green. Cl is high electronegativity, is highly electronegative. Electronegative. Therefore, the OH bond here, yeah, the OH bond in chloroethanoic is more polar, so weaker, therefore more H pluses break free. Stronger acid. Dissociate if you like. If you prefer dissociate, more H pluses dissociate if you prefer. Those people who really like the great chemistry. Explain why the data book volume do not usually contain Ka values for strong acids. Lol. That's funny. Why would it give a strong acid a Ka value? Strong acids fully ionize in water. Fully ionize in water. Lol. Yeah. Therefore, the Ka value would be massive. It'd be like 10 to the 20. It'd be mental. Ka value. I've seen them. You can actually get them. Ka value would be infinite. Would be infinite. Brackets, stupid, crazy big, stupid large. Lol. Oh, it's really chuckled me. I like that one. It's one of my favorites. 2 marks. Yeah, fully ionized Ka value would be infinite. You can actually get Ka values, by the way, for the strong acids. It can be done. So check this out. Ka for HCl. Oh, I want to see it. Hydrochloric acid 10 to the 6. It's absolutely massive. Look at that. So hydrogen sulfur. It's different. But they're huge. Absolutely huge. Nitric acid times 10 to the 1. It's interesting. I like that. They're very different, though, aren't they? That's not what I was expecting. I was expecting them all to be absolutely massive, like in the 10 to the 9s and way even higher. Oh, that's very interesting. How surprising. Table of acid-base strength. Huh. It's not interesting. It tells you that the sulfuric acid could potentially, it wouldn't though. That's so stupid. I don't like it. Large. Tiny. That's really interesting. I don't like that. I didn't realize that there would be such a big difference. I thought they would all be absolutely enormous. They fully ionize in water. I'm baffled by the sulfuric acid one. I would have said that would be way larger than what it is. Yeah, don't look at those values. I feel like they're confusing in some regards. Yeah, don't look at it. Ignore it. Anyway. So next, acid dissociation. A buffer solution is prepared using ethanoic acid and sodium ethanoate. In the buffer solution, the concentration of ethanoic acid and the concentration of sodium ethanoate is this. Calculate the pH. Wow, they've given us everything we need. Absolutely everything. H plus, sodium ethanoate. They've given us everything. Wow. The people are going to skip all the steps here and lose all the marks. That would be a disaster. Yeah? Rearrange for that guy. Yeah, Ka multiplied by the acid divided by the salt. And they've given us everything. I feel like there's a trap in here somewhere. 1 mark for that guy. Yeah, input my numbers. 1.74 times 10 to the minus 5 multiplied by the acid concentration. The concentration of the acid is this. Oh, you just run them in. I'm really surprised. Salt, 0.105 equals, there's going to be a mark for this guy, 1.7. Oh, so easily to lose that mark. That would have been an easy mistake, that, guys. You've got to use the value they give you. Exponential minus 5 multiplied by 0.186 equals, divided by 0.105 equals, and I get a number of 3.08 times 10 to the minus 5 minus log answer. pH minus log answer. pH 4.51, dead on what I always say. Look at that. Amazing. That was an easy one. Next. Oh, no. And that's why they gave us an easy one. That's why, because they're, oh, nuts. Okay, breaking buffers. Oh, I've got to keep hold of all these numbers. Oh, no. Okay. First of all, pH 4.51. Supposed to keep that over there. Okay, in a different buffer, okay, hang on. Well, no. It's a different buffer solution. In a different buffer solution, the concentration of ethanoic acid is this, and the concentration of sodium ethanoate is this. A sample of hydrochloric acid containing this many moles is added to 1,000 centimeters cubed of the buffers. Calculate the pH of the buffer solution after the hydrochloric acid has been added. You should ignore. Generally, do we just assume that they are taking the acid as the titrant without information? Good question, Ria. No, you look at the graph direction. You just look at which way the graph's going. I suddenly realized the graph's at the bottom. Yeah. They will always tell you which one's which. Okay, so first step. Sample of hydrochloric acid is added, and they're adding moles of it. Oh, that's clever. Guys, do you notice that? A sample of HCl is added, but there's no vol. Oh, isn't that interesting? And they've given us it in moles already. Oh, that's really clever. So actually, it becomes a whole lot easier. So the concentration, let's go for, let's do this bit first. I'm going to color code this. Ethanoic acid. So weak acid moles. Now this is clever because they've given us 1,000 centimeters cubed, which is 1 liter. And 1 liter means that the concentration is the same as the moles. Isn't that neat? I hope everyone's okay with that because it's number of moles equals C 0.251 times by the volume in centimeters cubed all over 1,000. It cancels out in my C times V over 1,000. So the moles is the same. Wow, they're doing some clever things here. So what's going to happen here? Need a roadmap. So the Ka equals H plus is the pH, then we've got the salt, and then we've got the weak acid. Right, what have I added? I've added HCl. The HCl is going to pull down the salt and increase the acid. Right, so the acid moles are going to increase plus 0.015 equals, that's the clever bit, guys, 0.251 plus 0.015. So that becomes 0.266 moles left over. That's increased. Now we go for the salt moles. And once again, we're in a liter. So the moles, the concentration they gave us, we can use directly as moles because they're the same number. So the moles equals 0.140, and the salt moles are going to decrease, minus 0.015 moles equals. So 0.14 minus 0.015 gives me 0.125. Now, they said you can assume that the concentration remains the same, but I'm still going to write down. So the conc of the weak acid is going to just be that number, equals 0.266, because we're assuming we're still in a liter. So the concentration of the salt is also the same thing, 0.125. Right, so now we can input these into this equation. Salt on top, reorganize. Ka, bring the weak acid over, times by the weak acid, all over the salt concentration. It's going to give me H plus. You can't skip any of these steps. So the Ka was given us to as 1.74 times 10 to the minus 5. So 1.74 exponential minus 5 multiplied by the weak acid. And the weak acid was here. Oh, it's just there as well. 0.266 equals, divided by salt, 0.125 equals. So that now gives me 3.70 times 10 to the minus 5 minus log answer equals. That's a really nice question. Really like that. And I get a pH of 4.43. And I can't compare that to the original because it was a different buffer. Interesting. Not allowing you to do any comparisons there. That's really mean, that. Don't like that. It's mean. Anyway, nothing matters. The value of the dissociation constant for benzoic acid. Write an expression for the acid dissociation constant Ka for benzoic. Ka equals H plus, square bracket. They will penalize you if it looks on the square, by the way, just warning you in your exam. O minus all over. And they're doing this because it provides us with our roadmap. Done. Calculate the pH of the benzoic acid. Ria, this is the false equation because it's simply a weak acid question. Yeah, this is just a weak acid question. So reorganize. Yeah, we can write the false one. Ka equals H plus squared all over the weak acid. We assume that the assumption is that all the H pluses come from the acid and not water. We also assume that the concentration of the original carboxylic acid remains unchanged considering the dissociation. So now we can input our numbers, reorganize as well. Root Ka multiplied, be careful, multiplied by the C6H5COOH. It's going to give us H plus concentration. Right, input my numbers. I'm going to use the same Ka value that we had in the previous question, 1.74 times 10 to the minus 5 multiplied by, where is it? It's given us the Ka. Oh, yeah, given the Ka. Oh, they're given us, there's the concentration right there, which is 0.012 root. Oh, hang on a sec. No. So easily done. Got to be careful. I'm using the ethanoic acid one. Silly Mr. Duncan. 6.31. That's K. It's a different acid, isn't it? Times 10 to the minus 5 multiplied by that root answer. So 6.13 exponential minus 5 times 0.012 equals root answer equals 8.70 times 10 to the minus 4. minus log answer. Minus log answer. pH equals 3.06. It's very reasonable. Next, a buffer solution with a pH of 4 is made using benzene carboxylic acid and sodium benzene carboxylate. Calculate the mass. Oh, this is much more interesting. Way more interesting. Calculate the mass of sodium benzene carboxylate that should be dissolved in 1 liter. They're being nice to us. They're being nice. Dissolved in 1 liter of this to form a pH of 4. Right, roadmap. Ka equals H plus. I've got the H plus because of the pH. Yeah, this is the benzene carboxylate. So this is the minus. Yeah, this is what we're after over the concentration of the benzene carboxylic acid. Much more interesting. Right, I've also got the Ka value and I've got that guy. So just reorganize it. The first thing I need to do is get the pH out. So I'm going to go 10 to the minus the pH. That's going to switch the pH into H plus. Yeah, that there equals H plus concentration. So 10 to the minus pH 4. Yeah, so shift log minus 4 gives me 1 times 10 to the minus 4. That's the concentration of H plus ions. Right, I've also got the Ka, which is there. So I can reorganize this for the salt. Bring that up to there. So Ka, which we can start inputting some numbers for, speed this up. 6.31 times 10 to the minus 5, multiplied by the concentration of the benzene carboxylic acid, which is there. Let's get rid of that circle, which is 0.012. So that's constant, and then I'm going to bring the H plus down all over 1 times 10 to the minus 4. That's going to give me the salt. Yeah, so 6.31 exponential minus 5 multiplied by 0.012 equals, divided by 1 exponential minus 4 equals, and I get 7.57 times 10 to the minus 3, and that's the concentration of the salt of the sodium benzene carboxylate. Sodium, I'll write it like this, C6H5COONA. That's the concentration in a liter. What that means is if this here is moles per dm cubed and we have 1 liter, it means that that is the same as the moles themselves. So moles is equal to 7.57 times 10 to the minus 3. Now, what the question has actually asked me to do is find the mass. This is grams over rams. And what they've done is they've given me the relative molecular mass, or formula mass because it's ionic, of the sodium benzene carboxylate. So number of moles is grams over rams. I'm after grams, reorganize. So number of moles times by rams will give me grams. Input my data, 7.57, I've kept it on my calculator, times 10 to the minus 3, times by, what was the MR? 144.0, right, multiplied by 144 equals, I need 1.09 grams, and I'm done. Clever game that. Like that one, that was fun. I wouldn't say fun, maybe I'm using the wrong words there. Next, oh, I've only got 3 minutes left. Right, so what I'm going to do, guys, is I'm going to leave it at this point. I'm going to leave it there today. And you've got you've got a couple of questions left to go. Not actually as many as I thought. Yeah, I'm going to leave it there. And you guys can have a go at those in your own time. And then ask me any questions later tonight or whenever in the next couple of days, because your test is on Wednesday. Start cam. Right, guys, I hope you found it useful. I'm available on Google Hangouts if you want to have a chat. If you have any questions for me. And I will speak to you guys soon. And if not, good luck on Wednesday. I'll see you then.